Hello and welcome to a maths high-level video. I'm going to talk about the properties of limits and in very particular about the squeeze theorem. If I have a limit of two things that are multiplying, for example, if I have the limit when n goes to infinity of n squared times e to the power of n, clearly what's going to happen is that when I substitute this n here by a very large number, I'm going to multiply the result of that times what I get when I substitute here for e to the power of n for the n for a very large number, which is why this is going to be equal to the limit when n goes to infinity of n squared times the limit when n goes to infinity of e to the power of n. And this is something that should be relatively logical. I mean, at the end of the day here I'm going to substitute the n for a very large number, multiply by e to the power of a very large number. So I could just do it separately. It's going to be the same thing. And the same thing applies for addition, division, and even for more things. For example, if I had the limit when n goes to infinity, or for example 2 to the power of, let's say, n minus 1. This is the same thing as 2 to the power of the limit when n goes to infinity of n minus 1. Why is that? Because again, I'm just going to substitute here for a very large number, right? Well, this is the same thing. So you just have to keep in mind a little bit the idea of how limits work. It's really not that complicated, but you just have to keep in mind that you can move around where the limit thing goes, and perhaps they're going to make your life a little easier. And now let's go for the squeeze theorem. So here's what the squeeze theorem says. If I have two sequences, an and cn, and I have one sequence bn that's always in between the two. Always in between the two, right? Look at it here. This is bn, goes down and up, but it's always in between an and cn. Always. It's always in between the two. Then it follows that if I have a limit for an and cn, and it's equal to L, it's the same one, you can see that both of these are going towards 0, then I can conclude that Bn will always go to that limit. So in this case, Bn will go to 0. It's a sandwich, right? We have An here going towards 0, Cn here going towards 0, and since this one is always in between, it must also go to 0. That's simply the squeeze theorem, and this is how we use it. We use it for difficult functions to evaluate, like this one here. Let's evaluate the limit when x goes to infinity of cos x divided by x. Now I know that cos x is going to be always smaller than 1 or bigger than minus 1, because that's the definition of cos x. So I'm going to simply do the limit when x goes to infinity of minus 1, which is going to be the smallest possible value of cos x divided by x. And if I do here the limit when x goes to infinity of 1 over x, I'm evaluating a function that's smaller than this one here, which is this one. It's always smaller or equal, and I'm evaluating one that's always bigger or equal, just this one here. Because 1 is always bigger than cos x. I know that this is always going to be smaller than 1, and I know that this is always going to be bigger than minus 1. Hence I evaluate these two, and I realize that indeed they give me the same answer. They give me 0. So I can conclude that the limit when x goes to infinity of cos x divided by x is going to be equal to 0. And that's the use of the squeeze theorem. Thank you very much for watching. I'll see you next time. Goodbye.